Hi everybody. This is the first video in a series of two about modeling, and in this video we are going to discuss time domain modeling. Modeling, well, we have two ways of modeling. The first way of modeling is the so-called white box approach. And in a white box model, we use theoretical analysis to get a relationship between the output of the signal and the input of the signal. And we do it by understanding of our process, so by deriving differential equations which describe the behavior of our system. Suppose in this example we have a container filled with water and water flows in over here and water flows out. And then we know that the change of volume in that container is equal to the water flowing in minus the water flowing out. That is white box modeling. We also have black box modeling based on experimental analysis. And in that way of modeling, we use input data and output data. So we put inputs to the system and we see how the system responds to that input signal or these input signals. And based on the output and input signals, we can derive the relationship between the output and the input, so how the model behaves, so what the system behavior will be. So in that case, knowledge of signal theory and system theory is really required. And the combination of both models, of course, provide the best results. So then you can verify a white box model by doing experiments, so by doing black box modeling. All right, so let's look to a kind of types of model analysis which we can use for experimental analysis. The first example is using a step function. Suppose we have a system over here and we don't know what's in it. We don't know how the system behaves. What you could do is you can bring the system into an operation point over here by setting a input set point to the signal and looking to the output. For instance, over here, this is my operating point. At an input of 10, the system has an output of 20. Now we are applying a extra step set point to the input. So we add that step function to the input signal and we see how the system responds to it. And based on that response, we can define what kind of system it will be, and we can calculate and define the missing parameters. That's the first method of experimental analysis in the time domain. What often is used in motion control is that we analyze our system in a frequency domain. And how it's done? Well, we add up some noise, white noise, to the input signal, and we look to the output signal, and by using the system identification toolbox of MATLAB, we can produce so-called frequency response function, FRF functions. And they can result in a Bode plot, which we can analyze, and based on that analysis, we can define what kind of system it will be. Well, that's not the topic of this video. This is about time domain modeling. And an assumption, no, another example about measuring in a frequency domain is using not only noise but specific sign function, which is also used in motion control systems when you're looking, for instance, for specific dynamics. As I said, we're looking to time domain analysis in this video. So suppose I have a system over here, a water tower for instance, and my process diagram looks like this. I could model it like a container filled with water and water is flowing in and water is flowing out. But I don't know anything about the system parameters. So what I can do is I put some inputs over here and I look to the outputs and I can derive my process and I can derive my process parameters. So suppose I put an input step to my function to my system over here, and my input step yields a maximum value of 4, so a flow of 4. Yeah, what the unit of flow will be in this example. So for instance, 4 liters per second. And I look to the output and I see that the output behaves like this. Well, when I see that, I could say, well, this looks like a first order behavior because I see something with a kind of an exponent coming to an end value. And when I know that, I can use the basic system function for a first order system, which is equal to k, transfer function is equal to k, a constant, times 1 over s times tau plus 1. And k is the static gain, and tau is the time constant of this function. So how can I derive these parameters, tau and k, from these measurements? Well, first of all, let's look to the k. And k is the gain in the static situation. And static means that nothing changes at the moment. So everything is static, is stable. So when nothing changes, then the derivative of constant values are 0. So in that case, I can set s to 0. So in a static situation, I can put s to 0, and then my transfer function is equal to h is k times 1 over 0 plus 1. So h is equal to k times 1 over 1. So my transfer function is only k. So in a static situation, I look to the input and to the output. I see the output is 4 at an input of 4. So my static gain is 4 over 4, which yields 1. So my static gain is k is equal to 1. Now let's look to the time constant of my system, and then I look to the 63% value of 4, which is almost 2.5. And at 2.5, I see that my value is 2.5 at the time, which is equal to 300 seconds. So in that case, my time constant is 300 seconds. So now I know everything about my first order system. I know the k, I know the tau. So I've modeled it by first order systems, and the parameters have been determined by measurements. So it's important to know your basic system. So you should know that this is a first order system behavior. Let's look to another first order example. This is an example in which we have an analog system which drives a motor. So I have a set point over here and a differential amplifier over here. And I measure the speed of my motor by using an encoder, and that frequency of encoder is transferred to an analog value. And that analog value is subtracted from my set point over here, and this probably has a gain over here, and that error is transformed to a PWM signal which drives through that voltage over here, the motor. So that could be my system. So I could make a model out of it, which looks like this. I have my set point over here. The differential amplifier, I have the subtraction over here. I have a gain over here, which is gain K1. I have a gain over here in my analog to PWM converter, which is gain K2. And then I have a PWM to voltage relationship over here. And then I have my system over here, system HP, which could be a motor with an unknown kind of mechanics connected to it. So perhaps there are mechanisms to the motor, I don't know, it's a black box. But I can measure the encoder speed of the motor, which is transferred by this component to a speed over here. So in order to be able to derive function HP, I could say, well, I make a cut over here. I set the voltage to the motor, and I look what the encoder value will be by transferring that to a voltage, which can easily be measured by using an oscilloscope. Well, we did that, and we have done the following. We have put a voltage over here of, let's say, about 6 volts to the input, and then the steady state speed transferred to the output voltage was a voltage of, let's say, 24 volt. And at a certain point in time, we put a step on it, a step to the input voltage, a step of 1, and we see how the system responds to it. So let's zoom in to that measurement over here. So we put a step of 1 volt to the system, and we see that the output changes from 24 volt to an output voltage of 28 volt. So, well, that is something which tells me or gives me information about the static gain of this system. What we also see is a behavior which really looks like a first order behavior, what we also saw in the previous example, because this is going to an end value by using a so-called E power curve. Um, we can see that this volt output voltage, so the speed of the motor is changing from 24 to 28. So we know in a static situation, by applying 1 volt, it yields an output volt of 4. So I could say, well, my static gain, just like in the previous example, is 4 over 1 is 4. So the K of my system could be 4. And I could also look to the 63% value of my end value between 24 and 28 voltage, and it is somewhere over here at 0.12 seconds after we start the input, the extra input to my system. So in that case, we could derive the time constant tau, and I could say, well, the tau is almost 0.12 seconds. So we know it's a first order behavior with a general transfer function like this. We derived the k. It was a static situation in which everything is constant, so I can set s to 0. My static gain is the transfer function in the static situation, which is k, which is 4 over 1. So I have a static gain of 4, and we have derived the time constant of 0.12 seconds. So also in this situation, we have seen that we can um, make an assumption, a first order assumption of the system behavior by knowing what the first order system behavior is, what the transfer function is, and we have derived the parameters k and tau. Now let's see what happens when we have a second order system behavior, in which we have a system, I don't know what kind of system it is, but at a certain point in time I applied a step of 5 to that system, and the system responses like this. And the first thing we see is we have overshoot, and that should trigger us. We should say, well, that could not be the case when we have a first order system, so probably this is second order system behavior. So now I can use the transfer function, the general form, the normal form of a second order transfer function for in which we have a couple of parameters which we should define. What I also see is that when I put a step of 5 to my system, well, I see in a static situation, my end value is 7.5, 7.4, sorry. So that could give me information about the static gain. And I see overshoot over here at a certain time. So that could give me also information about the other missing parameters. So first of all, let's look to the general system behavior for a second order system. And we have seen in a previous video that the transfer function for a second order system is equal to h equals a constant k, or kp in this situation, times omega 0 squared, which is the undamped natural radial frequency of the system, divided by s squared plus 2 times beta times omega 0 times s plus omega 0 squared. And remember that beta is a relative damping factor. And we've seen, well, we have overshoot, so the damping factor should be lower than 1. So that could be an extra check. So first of all, we determine the static gain. And we've seen that we can define the static gain as the situation in which we put s to 0, because static means nothing changes, so all the derivatives are 0. So we can put s squared and s to 0, and then my transfer function for the static situation is hp is kp times omega 0 squared divided by 0 plus 0 plus omega 0 squared. So we have this part in the numerator and this part left in the denominator, which is in a static situation kp times omega 0 squared divided by omega 0 squared, which yields only kp. So kp can be determined from the measurements, which is the static output value divided by the static input value, which was constant, and then we have the gain kp. So two parameters left, omega 0 and beta. We can define, or we can determine the relative damping beta when by looking to the overshoot. And the overshoot in the system is defined as the maximum value which we measured minus the static value, and that divided by the static value. So that is the relative overshoot. And perhaps you measure it in percentage, then you have to multiply by 100. So this is my overshoot definition from my measurement, what I can see from the measurements which we saw a couple of minutes ago. We also knew from the definition from a second order system that the overshoot can be defined as e to the power minus p times beta divided by the square root of 1 minus beta squared, perhaps times 100%. So beta is a relative damping coefficient, and by setting these two equations by using saying that this equation and that equation should be the same, then we have a measured value over here, and we can calculate the beta over here. So that gives us beta, which is one of the missing parts, missing parameters from my second order transfer function. So then we have one parameter left, and that is the omega 0. And the omega 0, the undamped angular frequency, can be derived from the equation that the omega, which is the damped angular frequency, is equal to the undamped angular frequency times the square root of 1 minus beta squared. Well, beta has been determined in the previous step. So now we have to define a method to measure or to calculate the omega, and based on the omega and the beta we can calculate the omega 0. Well, one of the ways to define the omega is by looking to the peak time, because the peak time, the time on which the maximum overshoot occurs, is equal to p over omega. So we can measure the peak time, and by using this formula we can calculate the omega. Then we have the omega, we have the beta calculated already, so omega 0 can be calculated by using this equation. It's omega divided by the square root of 1 minus beta squared. So then we have everything which yields the following transfer function. My transfer function is equal to Kp, the constant static gain, times omega 0 squared divided by s squared plus 2 times beta times omega 0 squared. Well, beta is known, omega 0 is known, plus omega 0 squared. And then we have all information left for defining our transfer function. Well, that's a quick video about system identification in the time domain. In the next video, we are going to look what we can do in a basic way in the frequency domain. Thank you for watching, and see you in the next video.